So we are going to move on to slide set 6. Yay. Right. So we've been doing reactions mainly with alkenes and alkynes. We've thrown in a few reactions where we make alkenes and alkynes. But this whole section is going to be focused on reactions at sp3 hybrid carbons. Right, so everything up until this point has mainly been either sp2 or sp hybridized carbons. Oh, real quick, on Friday, the video I put up on YouTube is every synthesis example from both sections. So some of them are a little similar, some of them are different. They might use a couple of different reactions. So if you wanted to go look at that, if you just like scroll through, I have a title card for each synthesis. So you can just like find like synthesis. You guys are 1 through 6. The late section was like 7 through 13 or 7 through 12. So you can go through and just find some more examples if you want to just look at more. All right. So, right, the types of reactions we're looking at, or things we're looking at, is we're looking at reactions where we have a leaving group Okay. So we're going to have some leaving group on our carbon, right? And so a leaving group is an electronegative atom or group that can be removed from our molecule. So it is a thing that is going to leave the molecule for the reaction to occur, right? The important thing about the leaving group, or one of them, is that it's electronegative. What that's going to do is that's going to lead to that leaving group being slightly negative, right? Because it's going to be pulling electrons towards itself because it's electronegative. And it's going to make the carbon it's bonded to slightly positive. And that polarization, the fact that the leaving group is negative and the carbon that it's bonded to is slightly positive, is going to allow all these reactions to occur. Right? We need that polarization. We need that negative positive to make these happen. Right? So we have two types of reactions that can happen here. You have a nucleophile, and that nucleophile will replace the leaving group. So you'll replace the leaving group with the nucleophile. This is called a substitution reaction. Right. So you're substituting the nucleophile for the leaving group. Right? These are sometimes you'll hear them called displacement reactions. The letter there, reactions. Right? The nucleophile is displacing the leaving group. Right? The nucleophile is knocking the leaving group off the molecule and taking its place. Right? And the other reaction that we can do, bless you. Yeah, COVID-19. Right, where you have a base and your base removes a hydrogen from a carbon adjacent from your leaving group. Right, and makes a double bond, generates the conjugate acid of the base, H base plus, and then your leaving group has left. This is an elimination reaction. So this is the reaction that we were doing at the end of the last set of slides to make alkenes, right? We were removing HX to make a double bond. So basically, this entire set of slides that we're going to go over is all the rules and considerations for substitution reactions. And then there's an entire other set of slides that is all the rules and different considerations for elimination reactions. So the next two set of slides are substitution now, elimination in like a week. And then we're like almost done. Right? Like there's this week. There's next week in your test on Friday, the 13th. Oops, sorry, that was not my intention. And then there's 2 days in your final. And we're done. So like there's only like 8 more lectures. Spooky. Yes.
I was asked about my plans for the final.
My goal for the final is to say that to hopefully have my stuff together. Yeah, we're recording this at PG-13. Have my stuff together for to have it up Thursday morning, and basically have it up from 8 a.m. Thursday till like midnight on Friday. I could maybe leave it up until Saturday. And then it'll probably be 2 or 3 hours. Where you just need to find a 2 or 3 hour window to take it. So Saturday, I could probably do till Saturday because I know people have to travel those days. So I don't want you have to like pay for like go in-flight Wi-Fi to try to take your exam. So, but I'm gonna give you a couple of days. It's not gonna be like a regular exam where it's just a day. I'm gonna try to give you like at least 2 or 3 days so you have some flexibility for travel and whatnot. I'm trying to look out, like whatever. Okay, so leaving groups. Yeah. For the vast majority of our reactions, our leaving groups are going to be halides. So you're going to have chlorine, bromine, or iodide. Right? Just like everything else, fluorine does not do these. We're going to learn one reaction with fluorine in the eliminations, and that's it. It's like one thing that fluorine does that you guys care about. There's a whole branch of chemistry that is just trying to make fluorine do stuff. because it doesn't want to do anything. But it's also a profitable branch of chemistry because, like, I think I've already showed you, right? Fluorine gets put into pharmaceuticals a lot because it replaces hydrogen. It can't get oxidized or removed. So if you have really good ways to put fluorines on things, it makes it so pharmaceuticals are easier to make. So that's why people pursue that kind of chemistry. Is there's a need for it in pharmaceuticals and other like materials and stuff. Okay, but yes, fluorine basically doesn't do anything. So you just have to worry about chlorine, bromine, iodide. All right, I've already touched on this, but right, so the carbon. The carbon leaving group bond is polarized, right? So like I said, this is going to be slightly negative. This carbon is going to be slightly positive. If you're a nucleophile, you want to add to the most positive thing that you can, right? So having your carbon leaving group bond to be polarized, that gives you a positive carbon for your nucleophile to add to, right? If that carbon is not positive, the nucleophile doesn't know where to go, right? It has to have a positive carbon to want to add to. Is this important also for elimination? So this is substitution. So having that partial positive charge makes it so the hydrogens on your beta carbon, right? So this hydrogen here is more acidic than it would be if that partial positive wasn't there, right? So again, having that partial positive charge allows your base to be able to react. If that partial positive wasn't there, the base wouldn't be able to remove the hydrogen. So having that partial positive charge helps both your substitution and your elimination reactions occur.
I gotta ask what my shape that I kept drawing that looks like an open 8 is, and it's a really bad lowercase delta. I'm sorry.
Oh, sorry. Yeah, this is my attempt at a lowercase delta. So that is a lowercase delta. So the delta means partial. So delta plus is partial positive. Delta minus is partial negative. So yeah, my open-sided 8. My handwriting A plus. I mean, I'll take the hate. Like whatever. I'm 40. I've had crappy handwriting forever. All right. So mhm. All right. So there are two mechanisms that substitution reactions go through, and they are kind of wildly different, right? You have the SN2 mechanism, or you have the one mechanism. Right, so your kind of base SN2 mechanism you have your leaving group, you have your nucleophile, and in a single step, your nucleophile attacks the carbon that has the leaving group and pushes the leaving group off the molecule. So in a single step, you break your carbon leaving group bond and you make your carbon nucleophile bond. Okay, so this is in a single step. All right, so this happens in a single step. The nucleophile will push the leaving group off the molecule. So the nucleophile adding to the carbon that has the leaving group pushes the leaving group off the molecule. Right? Little intuition here. If you're going to push someone down a hill, would you approach them from the front or from behind? From behind, right? Nucleophile does the same thing. Nucleophile has to push the leaving group off the molecule. The nucleophile has to sneak up on the leaving group. So it has to come from behind the leaving group and then push it off. Bless you. I got behind my little blast shield. I'm safe here. All right. So SN2 reactions are a single step. Nucleophile pushes the leaving group out, and the nucleophile has to approach from behind the leaving group. SN1 reactions. The first thing you're going to notice here is in the SN2 reactions, the nucleophile is charged, right? It was Nu minus. Here, our nucleophile is neutral. It has no charge. So what happens first is not that the nucleophile pushes the leaving group off. The leaving group leaves on its own.
I gotta ask why the leaving group just leaves.
So what happens is in a polar enough solvent, the carbocation becomes stable. And so the nucleophile, the leaving group will dissociate from the carbon, but they'll hang out close to each other so they can remake that bond where they come off and go back on, come off and go back on. And eventually the nucleophile can come in and intercept that carbocation. It's just energetically possible, so it can happen. And then we take advantage of it by adding enough nucleophile that we can outcompete the leaving group adding back in. So now your nucleophile, which is something that normally is going to have just has a lone pair. Right? It doesn't need to have a charge as much as it just needs to have a lone pair. Can add to that carbocation and make the product. Yes, it is easier. The first way is easier, but depending on what your leaving group is, what your nucleophile is, both are possible. Right? So SN1 reactions are 2 steps. That's right, you should be angry. SN2 is 1 step. SN1 is 2 steps. We're going to go over it here in a second. Yes.
So it says, how does a nucleophile have a lone pair but not have a negative charge?
So it's the nucleophiles, the reason they have lone pairs is it's something like an alcohol, right? Where your oxygen has lone pairs, but is neutral, right? Isn't negatively charged. Where in like an SN2 reaction, it would be something like O would be an alkoxide where you've removed that hydrogen. So, right, the thing with the O minus is a stronger nucleophile, right? It wants to get rid of its negative charge, so it wants to add to something more than the uncharged version, right, that just has a lone pair and is happy, but will add to something because it has electrons. Right. So an SN1 reaction is 2 steps, right? Makes a carbocation. So you should get twitchy because you're like, oh, that means there can be rearrangements. Ugh. Never forget. Right. And the leaving group, leaves first. Right. So you have your leaving group leaves, makes a carbocation, then your nucleophile adds. Right.
So I got asked, what types of groups are leaving groups?
So our leaving groups are initially going to be chlorine, bromine, iodide. It's going to cover like 99% of the leaving groups are going to use an organic 1. And then we can do a couple different things in organic 2. But you need to think chlorine, bromine, iodide are going to be the vast majority of your leaving groups. So just halogens right now. Right? So how do you pick a mechanism? And this is what a lot of what we're going to go over in the next 24 slides is going to be about, is knowing how you pick which mechanism, right? So the first is the structure of the leaving group. I have on the slide alkyl halide, right? Since most of our leaving groups are halides, right? Is that leaving group primary, secondary, or tertiary? That's going to impact if we're going to do SN1 or SN2, right? So the structure slash charge of the nucleophile is the other thing we need to look at, right? So we need to look at the structure of the halide, we need to look at the structure of the nucleophile. So I'm going to basically explain everything you need to know about SN2 reactions. Then I'm going to explain everything you need to know about SN1 reactions, and then I'm going to tell you how you tell the difference between SN1 and SN2. And then when we get to eliminations, I'm going to tell you how you tell the difference between if you're doing a substitution or an elimination. All right. right? Regardless of which mechanism that you're using, right? If you're using SN2 or SN1, if you're doing a substitution, at the end of the day, you are replacing your leaving group with your nucleophile, right? So regardless of what mechanism you're using, the outcome is kind of the same. You're like, oh, I'm doing a substitution. The thing that I've deemed as my nucleophile has to replace my leaving group. How you get there changes, and it can impact stereochemistry and things like that. But the overall big picture of the reaction stays the same. And I got people falling asleep in here. I'm not throwing candy today, so people are less motivated and more sleepy. She's so crafty from Friday. Well, I had leftover candy, so my lunch was I just ate mini candy bars. So I actually had a meal that contained all the food groups in my fridge, and instead I ate a yogurt and like 12 mini Hershey bars. Yeah, the yogurt made it healthy. It was fine. It was great. It was just the topping. Yeah. All right. So we're going to start with the SN2 reaction. So we know the mechanism of an SN2 reaction based on kinetic data, which I know when I say kinetic, everyone goes to like the darkest point in Gen Chem 2. It's like ugh, ice tables. Ugh, no, don't worry, we're not going to do anything like that, right? So, right, kinetics, if you remember, reaction kinetics. Right, measures the rate of the reaction and what impacts that rate, right? So we're talking about reaction kinetics, we're talking about how fast the reaction is, and then what we can do to change how fast the reaction is. Right, for an SN2 reaction, the equation that defines the rate is as follows. So the rate equals some constant k that I don't care about. Right, so the rate is some constant k times the concentration of the alkyl halide times the concentration of the nucleophile. Right? So if you remember, this is a rate law. This rate law depends on the concentration of two things. So it is second order. Right? The rate law overall is second order. Right? What we care about in the rate law, what matters for us, is that a rate law tells you how many molecules are in the transition state for the rate determining step. For your biology people, you feel at home. There's just a bunch of random letters and abbreviations. Like, excellent. Just to give you that full experience. There you go. All of biology. Green circle and blue box that has a hole that fits green circle. There we go. So, what this rate law is telling us is that in the transition state, we have both the alkyl halide and the nucleophile. So in the slowest step of our reaction, both of these are present, right? It's not just one or the other, you have both, right? Since the rate law depends on two things, the reaction is bimolecular. All of the stuff I just went over explains why an SN2 reaction is an SN2 reaction, why it has that name, right? The S is for substitution. The N is for nucleophilic, right? Because it's a substitution that requires a nucleophile. And the 2 is because the transition state for the rate determining step is bimolecular. It has 2 molecules in the transition state. Wow, yeah. Thanks, Owen Wilson. Wow. So, what are some features of SN2 reactions? So you can't spell. Right? So the rate depends on the concentration of the alkyl halide and the nucleophile. Right? That means if we have 2x halide, that equals 2x the rate of the reaction. Right? So if we double the amount of alkyl halide we have, we double the rate of the reaction. Double the amount of nucleophile, double the rate of the reaction. Right? This is where we walk up to the line of doing math. Right here. This is it. All right? So you have a reaction, right, where you have your rate, Right, we have our little rate law. Same thing we just had. And you have a rate of 1, 1, and 1. Right, so your rate is 1. Your concentration of alkyl halide is 1. Your concentration of nucleophile is 1. Cool. What would my rate be if I tripled the amount of alkyl halide? It'd be 3 times as fast. What if I doubled my alkyl halide and cut my amount of nucleophile in half? Still 1. What if I cut them each by half? It's 1/4. This is as close to math as we get. A half of a half is a quarter. Yes. Yes. I contend this is not math because if I was like, hey, second grader, 3 times 2, I'd get a song and I'd get 6. Right? They might have to go through the whole times table with a little song, but I will get the answer and entertainment. So not math. All right. So there's like a question like this that's on the homework for sure, right? But so since it depends on both the alkyl halide and the nucleophile, changing either one is going to impact the rate of your reaction, right? With yeah. Yeah, we'll just make it generic X. So if I go from a methyl halide, right? This is fast for an SN2 reaction, right? Hydrogens are the smallest atom on the periodic table. If you're a nucleophile, right, it's really easy to get to the carbon that has the halogen on it, that has the leaving group on it, because you're going by the smallest possible thing you can go by, right? Offers no resistance. As you replace those hydrogens with carbons, the reaction gets slower, right? Because carbons are bigger than hydrogens. He doesn't have space here. So we go from we go from methyl, which is the fastest. Then we go to primary. We add 1 extra carbon. It's harder to get to the carbon that has the leaving group on it because there's a bigger group there. Then we go secondary. Now there's 2 larger groups. It's harder still to get your nucleophile to the carbon that has the halide. There we go. It has the halide. And then when you have a tertiary leaving group or a tertiary halide, you can't do an SN2 reaction on a tertiary carbon because there's just too much bulk on that carbon for the nucleophile to be able to reach the carbon that has the leaving group. Right. Sure.
I was asked to repeat the last explanation.
So when you get to having 3 carbons, when you get to a tertiary carbon, right, a tertiary halide, your nucleophile can't get to this carbon anymore because all the other carbons around it are blocking the approach. So the nucleophile can't get to it. It's going to do something else because it can't get to that carbon. Bodyguard, I just think as a bouncer, right? Right. If you're like 5 foot, like 95 pounds, Tong East is not going to hire you to be a bouncer, right? Right. You're going to be like, you can't come in here. And sometimes they like pick you up, move you, set you down, and like go in, right? You're like 6'5", 6'6", 350. You can't come in here, and people are like, I'll listen to you, right? Same thing, right? As the bodyguards or as the bouncers on the carbon with the halogen get bigger and more numerous, the nucleophile is like, sure, I can go by hydrogen, out of my way, hydrogen, do reaction. It gets a little bit harder when the hydrogen gets replaced with something bigger. It gets a little bit harder when there's 2 bigger things. And it's just like, yeah, I can't get by here when there's 3 big things. I'll go somewhere else. I'll go do something else. I'll go to the coop. They don't card either. It's fine. Right. The other thing is you get inversion of stereochemistry with SN2 reactions. So what that means, let's say my halide is up and I have my nucleophile. Since to do an SN2 reaction, you have to approach via backside attack, right? You have to come from behind the leaving group, behind your halide. If your halide's forward, behind your halide is coming from the back, right? Is you end up being dashed. Right? So if your leaving group's pointing forward, the nucleophile has to come from behind. If your leaving group is back, your nucleophile has to come from the top face. Right? So you're always going to invert your stereochemistry when you do an SN2 reaction. So a wedge is going to become a dash. And this only happens at the carbon that has the halide or has the leaving group. If there's other chiral centers in the molecule, they're not changed. It's only the carbon that you react with. So if we were to have right, the carbon that we reacted with, our nucleophile, is going to invert the chiral center that we reacted at, but any other chiral centers in the molecule, nothing happened, right? Nothing happened to those carbons, so there was no reaction. Right? And so the reason this happens, right, is since the nucleophile has to push the leaving group out, it has to come from the opposite side. So you're always going to just turn that carbon that has the halogen on it kind of inside out. You're always going to come from behind. Right? So another thing is sterics around. So if you have big groups not directly on the carbon that's reacting, but around it, that will slow your reaction as well. So let's say we had this versus that. The group that has the quaternary carbon beside the carbon you're reacting with would react slower, right? Because this tert-butyl group right here is much bigger than this ethyl group. Right, so it's harder to get past that tert-butyl group than it is to get past the ethyl group. Okay, quick fun story, because I think we're done. So I was at Target, had a hat on, hair wild, puffing out, a mask on. I saw 4 girls get into a car. One girl's wearing a lacrosse shirt, and she looked like a former student. But she had on a mask, and I was like, Haley? And she looked at me, we made eye contact, because I could only see her from the eyes down. I was 100% sure it was her. Since I looked like a homeless person, she had no idea who I was. And like she just looked at me, I looked at her, and we both realized it was awkward, me more than her. And then she just got in her car, and I was like, looking, I was like, I feel like I know you. And then like they drove past me and looked at me like, is this homeless person following us? He's like, no, homeless person just going to the Target. I was just like, oh, this is super awkward. I'm sure they went to like some party on Saturday and it was like, this weird homeless guy. And it's like, no, this was your former professor, I'm pretty sure. Oh no, like I will like stop and talk to students. I when this all started in like March, I saw a student had class and I was like, why aren't you wearing a mask in like March? I'm like, these are dark times. Get out of my Target without your mask on.